You've seen AI write Python functions, build React components, fix bugs in seconds. It looks like AI has coding figured out, but try asking it to write a CUDA kernel for a GPU. Here's what happens. The AI sets the grid Y dimension to 262,144, but the GPU hardware limit is 65,535. The kernel crashes. It didn't know about the hardware constraint. This isn't a fluke. The best coding models in the world score below 30% on industrial code benchmarks. There's a massive gap between AI that writes Python and AI that writes code for real hardware. Ask it to generate Verilog for a chip design, and the simulation fails. Ask it to write embedded C for a microcontroller, and it references hardware functions that don't exist. These aren't edge cases. This is what happens every time you push AI coding beyond web development. A team of researchers just published a paper trying to close this gap. It's called InCoder-32B, and it's the first coding model built specifically for industrial scenarios. So why does AI struggle with industrial code? The first problem is training data. GitHub has hundreds of millions of Python and JavaScript files. That's what coding models train on. But Verilog for chip design? That's written by hardware engineers at Intel and Qualcomm, sitting behind company firewalls. CUDA kernels? Written by GPU specialists at NVIDIA. Embedded C for ARM microcontrollers? Locked inside firmware teams at automotive companies. The models have barely seen any of this code. Second, the correctness bar is completely different. A Python script either runs or it doesn't. But industrial code has to pass through real verification pipelines, and there are 4 major domains where this matters. Chip design. You write Verilog, a hardware description language. Your code goes through behavioral simulation to check if the logic is right, then logic synthesis to map it onto actual gates, and it has to meet timing constraints on real silicon. If a single signal arrives 1 nanosecond too late, the whole chip fails. GPU optimization. You write CUDA or Triton, compile it with NVIDIA's toolchain, and run it on the GPU. The kernel has to produce numerically correct results and run faster than the baseline. Getting the right answer slowly isn't good enough. Embedded systems. You write C, cross-compile it for an ARM chip like the STM32, and test it on a full simulator that models every GPIO pin, every interrupt, every timer, and 3D modeling. You write CAD query scripts that produce solid geometry. The output has to be a real manufacturable shape, not just valid syntax. In every case, the code isn't just running in a sandbox. It's being tested against the same tools and environments that real engineers use in production. That's why general-purpose coding models fail here. They've never been trained with that kind of feedback. InCoder-32B tackles this with a 3-stage training pipeline they call code flow. Stage 1 is pre-training. Since industrial code is scarce, they had to get creative with data collection. They pulled from public repositories, scraped technical documentation, and even used OCR to extract code snippets from engineering research papers and textbooks. After cleaning and deduplication, they pre-trained a 32 billion parameter model on over 4,000 GPU chips. Stage 2 is mid-training, and this is where it gets interesting. They progressively extended the model's context window from 8,000 tokens to 32,000, then all the way to 128,000. At the same time, they synthesized industrial training data. They worked with real hardware engineers to write realistic scenario specifications, generated seed code, and created question-answer pairs verified by actual simulation. They also included agent trajectories, multi-step debugging sessions where the model interacts with compilers and simulators and learns from the error feedback. Stage 3 is post-training. This is the key part. They built dedicated simulation environments for each of the 4 domains. Every piece of generated code gets compiled, executed, and verified in the real toolchain. If it fails, the error message goes back into the model to generate a repaired version. This closed loop, generate, verify, repair, is what makes industrial code training fundamentally different from normal fine-tuning. So, does it actually work? On general coding benchmarks, InCoder-32B holds its own against models 3 to 15 times its size. 74.8% on SWE bench verified, 49% on live code bench. It's competitive without sacrificing generalability, but where it really stands out is industrial code. On chip design benchmarks, it achieves the best open source results on RealBench by a wide margin. On GPU kernel optimization, it leads all open source models on kernel bench across all 3 difficulty levels. And it even beats Claude Sonnet 4.6 on some metrics. On 3D modeling, same pattern. 132 billion parameter model covering 4 industrial domains that previously needed completely separate tools. But this isn't a solved problem. The researchers analyzed nearly 2,000 failure cases and found clear patterns. The most common failure is compilation errors. The model generates Verilog with malformed port declarations or embedded C that references hardware functions that don't exist. It's learned the vocabulary, but not all the rules. When code does compile, the next problem is functional correctness. 79% of repair benchmark failures produce code that compiles fine, but fails the tests. The logic looks right, but the behavior is wrong. And on optimization benchmarks, a third of failures produce code that works but isn't fast enough. The paper's own conclusion is honest. There is still a long journey ahead. Here's why this matters. The chip in your phone? Designed with Verilog. The GPU kernel that trained the AI model you used this morning? Written in CUDA. The microcontroller in your car's braking system? Running embedded firmware? The 3D printed part in your headphones? Generated from a CAD script. This is the code that builds the physical world, and until now, AI couldn't help write any of it. InCoder-32B is a first step, not the last, toward AI that reasons about hardware constraints, timing budgets, and real-world verification. It doesn't solve the problem completely. There's still a long journey ahead. But it shows that with the right training data and the right verification pipeline, that massive gap between writing a Python script and designing a chip can start to close.